So I'm going to show a few projects today, probably more than I have time to, but a few projects from Bureau Happold that show how we manage information and the sort of tools that we need to create and the simulations that we undertake to solve some very complex challenges. To Jane's point earlier, which was really nice of a data tsunami, the first image you're going to see here is not a photograph. This is a 3D laser scan of the inside of a hangar at JFK, where they've stored the remnants of the World Trade Center. We were tasked with forensically reconstructing several of these to do an analysis model for the re-erection of several of these tridents in the World Trade Center Visitors and Orientation Center. So this image shows you the level of detail of data that we get out of these kinds of laser scans, and are going to be very typical going forward of how we do as-built dimensioning of information and Radiohead videos for those of you who are fans. In any case, from this, you need to be critical about the way that you design tools. So we designed tools not only to extract exactly what we needed in terms of the point cloud information, but to reconstruct the surfaces so that we had only the critical bits that we needed in order to conduct proper analysis. And that is a very tricky thing to figure out what you need to sort of throw away and what you need to keep, and especially how to write the software to deal with this massive information. In a roof structure like this in the United States Institute of Peace by Moshe Safdie and Associates, we had to take 47 different load cases on several hundred panels, on a couple of hundred different load cases, which generated a ton of analytical information. Being able to not only handle that amount of analysis over that many load combinations, but also then to use that same model as the centerline geometry from a BIM model, which went straight to the fabricators. And this is a view from the webcam, I think yesterday. Again, this talks about the sort of massive information that we have to sort through and the tools that we are going to have to write, because it's not going to be software off the shelf. The Cooper Union, the new academic building by Morphosis, we worked on the sculptural atrium. This was an example of where we had to distill data into something super simple. Guys in the field had to be able to cut this thing with chop saws and weld it together with a welding rig using only plumb lines. So we had to write software to filter through this entire thing and provide nodal coordinates for each one of those intersections that they could get with plumb lines. Turned out pretty well. In the case of this roof, again with Moshe Safdie and Associates for the Crystal Bridges Museum of American Art, to James's point about rule-based modeling, this entire structure is developed from a series of rule-based components. So we sit with the architect, we develop the rules, and then we write a series of programs that instantiate all the geometry using those rules. So recreation of elements or fixing of elements, or this quick iteration, is a simple aspect of changing the rule basis and reinstantiating the geometry. It's a completely different way than the current mentality in 3D modeling, which is to remodel, remodel, remodel. In the case of the Saudi Aramco Cultural Center, these 5 buildings in the desert, which they wanted to clad with stainless steel tubes, 70 millimeters in diameter with a 10 millimeter reveal, hundreds of miles of stainless steel tube cladding these. We needed to write an algorithm that offset these curves for the center lines of these steel tubes using something that looks like your thumbprint. So here you see a bit of the algorithm on the left. Furthermore, we had to write another series of program that took window stripes out of this building, and where the windows passed across that geometry, we needed to cut those center lines and flatten the tubes so that they were fins. So when you were looking out the windows, you were looking through fins instead of a wall of stainless steel tubes. And all of this is possible because in the end, the fabricators use a 3D tube bending machine, which takes our IGES curves directly out of the model, and they're able to build entirely in 3D these complexly curved components and then panelize the entire structure for installation. This is GIG. For U2's 2009 tour, we designed, along with Chuck Hoberman Associates, an 80-foot tall expanding Jumbotron, which is essentially a Jumbotron that's the size of a building and it moves. So we use Chuck Hoberman's data, their kinematic paths for the opening, the operability of this to define our nodes. This is one of 24 of the long vertical sections of this screen. And remembering also that this screen is meant to be broken down in a day and taken around the world for 2 years, around and around and around. And on top of each one of those hexagonal panels is an LED panel that becomes part of the Jumbotron. So you can imagine, the amount of data that's generated from this not only being a static structure, but also being something that's operable. So you have to analyze it in several different conditions. It's movement state, it's closed state, it's open state. So again, a lot of custom software. With the artist Janet Eckelman, we did a series of pieces involving fishing nets, which sounds very strange, but Bureau Happold's sort of history of doing form-found and tensile structures, we wrote a series of programs to help her break down these complex shapes that they gave us into analysis models, also to create looming diagrams, because sometimes you're not actually outputting to a fabricator who has any 3D capability or high-tech fabrication. You have to output to what he has. So in this case, it's a 1950s era fishing net loom with one dial. So you have to order the information in a way that he can use. So that in the end, this is stationed above a public plaza in downtown Phoenix, Arizona. That top ring is about 100 feet in diameter, and the entire sculpture is about 50 feet tall, comprised of some several hundred miles of polyester twine. And then finally, and Luke promised me he would hold me on the slide for just 1 second, this is what, to Dean Wigley's point, I think is really the future. This is work that I'm doing here right now with David Benjamin at the architecture school, which looks at giving students the power of not only structural analysis, but parametric modeling and multi-objective optimization to actually start looking at solutions and evolving solutions that are more fit from the beginning, instead of the sort of current track of we design it as architects and then hand it off to you engineers and say, make it stand up.